This will be a discussion about radiation and how we can detect it by using a cloud chamber. Before we begin, it would be a good idea to refresh our memories of what we mean by radiation, like what it is, and a few of the characteristic properties of the different types. As we know, radiation is the result of radioactive decay. This is where an unstable nucleus emits something in order to become more stable. This something that is emitted depends on the nucleus and what exactly is making it unstable. If the nucleus simply has too much energy, it decays to a lower energy state by emitting electromagnetic radiation, usually in the form of gamma rays or X-rays. If the nucleus is unstable because it is simply too big, stability is approached through alpha decay, the emission of an alpha particle. Similarly, if the nucleus has too many protons or neutrons to be stable, it will undergo beta decay, emitting a beta particle. This is a Segre chart, in which the number of protons in a nucleus is plotted on the vertical axis, the number of neutrons plotted on the horizontal. The black squares indicate stable nuclei, those which do not undergo radioactive decay. The areas of the graph which are of interest to us are the pink, blue, and yellow areas, as these are all populated by radioactive nuclei, which we will discuss later. As mentioned before, alpha decay occurs when a very large, unstable nucleus emits an alpha particle. Due to the mass lost by the parent nucleus, that is, the initial unstable nucleus, it gains stability. To understand why a massive nucleus becomes more stable following mass loss, consider the following. We know that iron is the most stable nucleus, and when we consider this graph we see why. The higher the binding energy per nucleon in a nucleus, the more stable the nucleus is. This is because when it takes a lot of energy to pull a nucleon out of a nucleus, the likelihood of radioactive decay is very small. Alpha decay allows a very heavy nucleus, one with a high mass number, to move towards iron from the right, thus increasing its stability. During an alpha decay process, the parent nucleus, here given the symbol theta, loses 2 protons and 2 neutrons to become the daughter nucleus, here given the symbol phi. Because mass and charge must be conserved during a physical process, the 2 protons and 2 neutrons must be emitted as well, as we saw in the video. This collection of protons and neutrons is called an alpha particle. A quick check of total mass, total number of protons and neutrons, and total charge tells us that this is an allowed process. As mentioned before, all nuclei want to be stable. Everything in existence wants to find the lowest energy state available. That's why things fall through potential fields. They are looking for the point which allows them their lowest potential energy. Likewise, the very heavy nuclei which undergo alpha decay do so to move towards the black squares on the Segre chart. Because the emitted alpha particle carries 2 protons and 2 neutrons away from the parent nucleus, the daughter nucleus is going to be 2 squares to the left of the parent and 2 squares lower down. Hence, alpha decay moves nuclei in this direction across the Segre chart. As an alpha particle is 2 protons and 2 neutrons, it is in fact identical to a helium nucleus, an atom of helium with its electrons stripped from it. We know that the mass of the alpha particle will be 4 atomic mass units, and its charge will be 2+. From observations, we know that the range that an alpha particle can travel is short, and that they can be screened completely with a sheet of paper. We also need to consider the ionization capabilities of an alpha particle. Because they are such massive particles, compared with electrons, any collision between an alpha particle and another atom will very likely result in that atom being ionized. The alpha particle smashes the electron free from its atom. Likewise, the strong charge also means an alpha particle passing close by to an atom will likely ionize it. The electron pulled off by the strong electric field of the alpha particle. These two factors considered together means that an alpha particle tends to ionize approximately 10,000 atoms following its emission. This large charge and mass of the alpha particle is described in terms of collisions as the alpha particle having a large cross-section, i.e. it has a large probability of reacting with anything in its path. Moving on to beta radiation now. There are actually two types of beta decay, beta minus and beta plus. Beta minus decay occurs in a nucleus with too many neutrons to remain stable. The nucleus will be found to the right of the stable atoms in the Segre chart. Beta plus occurs in nuclei with too many protons for stability. These nuclei will be found vertically above the line of stable atoms in the Segre chart. During beta minus decay, a neutron within the parent nucleus, again with the symbol theta, spontaneously changes itself into a proton, and an electron is emitted. The emission of the electron is to maintain charge conservation. During beta plus decay, a proton within the parent nucleus, again theta, spontaneously changes itself into a neutron, and a positron, the electron's antiparticle, is emitted. This is again to maintain charge. Note that in each case there is no mass loss by the nucleus, as we would expect for simply a conversion. For anyone who is concerned about where the electron and positron have come from, remember that the masses of the proton and neutron are subtly different, although when expressed in atomic mass units they are the same. The difference in their masses is so small that it can be ignored. Such is the case for the mass of the electron or positron. The mass is so small when expressed in atomic mass units that it can be ignored. Again, radioactive decay occurs only when the daughter nucleus is closer to the line of stability than the parent. As beta minus and beta plus decays involve the changing of a neutron into a proton, or vice versa, the daughter nucleus of a beta decaying parent nucleus will either be diagonally up and left for beta minus decay, and diagonally down and right for beta plus decay. Now, we know that beta minus particles are in fact electrons, and beta plus particles are positrons. The different names indicate that they are decay products, and not electrons or positrons arising from any other physical processes. We also know that the mass of the beta particles, which will be the same for both beta plus and beta minus, is enormously smaller than the atomic mass unit. In fact, it is 1/1800th of a proton mass. As they are electrons, or positrons, we know the charge carried by a beta particle will be +1 for a positron and -1 for an electron. And due to their small masses and charges, beta particles have a small cross-section, but they do move a lot faster than alpha particle. Due to this, they will only ionize around 100 atoms each, but will also travel considerably further. The small cross-section of the beta particle means that they can travel through materials significantly more successfully than alpha particles. That is, while alpha particles are stopped by a paper screen, beta particles can pass through that screen, and need a foil of metal to fully stop them. They are said to be more penetrative. Following our revision of the different types of radioactive decay particle products, we will move on to a quick discussion of a cloud chamber, a very intuitive and visually powerful method of tracking and detecting radioactive decay particles. A cloud chamber is, at first glance, an empty transparent box. However, we know that in this condition nothing could be observed using the chamber, so there must be something more. The bottom of the chamber will be cooled, with the top either held at a higher temperature by a heater, or simply the ambient room temperature. The chamber will in fact not be empty, but will contain a vapour, although in the gaseous form the vapour will be transparent as well. Ideally there will be no dust or water vapour within the cloud chamber, as they adversely affect the quality of detection. These are the only conditions required for a working cloud chamber, although before we can use one we need to understand a little more of the physics of the workings. This is an example of a cloud chamber. We can clearly see the transparent walls. The base plate of the chamber will be cooled in some way, usually by having a refrigerant pumped under it, quite like the way a refrigerator works. The light at the front of the image provides illumination, which is quite important to a cloud chamber, but not vital to its operation.